Okay, guys, so today we're going to talk about 9.4, which is exponential growth and decay functions. So the best way, so I'm going to show you a formula for this, and this will be the formula we use for problems like this. So we're going to talk about exponential growth, and we're going to talk about exponential decay. So for me, the best way to do this is just to do some example problems so you can kind of see how it works. You can look at a graph of it. We can look at some features on the calculator that might be able to help us, and also how to work with the calculator in finding out the answers for these problems. So exponential growth and decay. So a quantity that grows or decays by the same percentage at regular time periods is said to have exponential growth or exponential decay. And it's growth if it's getting bigger and decay if it's getting smaller. So there are many real life examples of exponential growth and decay, such as population, bacteria, viruses, radioactive substances, and so on. Okay. So this is what we're talking about. So we have our exponential function like this, right? And we see that it kind of works like this. So what exponential growth and decay is we're going to kind of build on this formula. Okay, we're going to build on this, or not on this formula, on this function. Okay, so if we're going to model exponential growth, okay, we're going to use this formula right here that says that y equals c 1 plus r to the x, and that'll be for growth. And then y equals, and we'll have this a little bit later in the slide, c 1 minus r to the x. So this will be growth, exponential, and this will be decay. All right. So if you notice here, okay, so it talks about right here on C, that's our initial amount. So that's the initial population. In some problems, like we were working in the interest rate problem, it had a P for principal amount. But in this problem, they're going to call it C, or capital C. Then they say 1 plus R. Okay, so if you remember in the previous problem, it was A equals P times 1 plus R over N to the n times t. So it's still very similar to that, but we're replacing n times t with x. And we're going to replace r over n with r, okay? Because we're not going to do number of times compounded or anything like that for interest rates, but it has a similar feel to it, okay? So it says that 1 plus r is the growth factor and r is the growth rate. So whatever number this is in the problem we're going to work on, the problem will be y equals, and then it'll have, some c, and it'll tell you that it's 1 point, oops, I forgot how much. Oh, it's 1.12 to the x. So that means that the growth factor is 1.12, but the growth rate is 0.12. So we'll talk about that in the next problem. And again, that's why I feel like practicing these using examples, because they're all basically word problems, is the best way to kind of talk about it. So, oh, and X is the number of time intervals as well. Okay, so it says in 2010, the town of Lacombe had a population of 25,000 and started consistently increasing by 12% per year. So you see how it's saying consistently increasing by the same percent per year. That means that we get to use our population growth model, okay, our exponential growth. If this yearly increase continues, predict the city's population in 2025, round to the nearest whole number. So we just want to fill in this table. So we need to find this, we need to find this, we need to find this, and we need to find this. So what we could do is we could do the calculation. So we could plug what we know into here and do the calculation for each one of these, okay? So if I wanted, I could say, our formula says y equals, and let's do year one. So 2011 is actually year one because they're starting it in 2010. So 2010 is actually year 0. Okay, so 2011 is the first year after that. So that'll be our x equals 1, 2012 will be our x equals 2, so on and so on. So what we're going to do is we're going to use 25,000 for our initial amount, right? And then it's 1 plus 0.12 because they told us 25,000 is our C, right? This is my big C right here. This 12% is my R. And then it's 1 plus 1, and then we have our X right here, okay? So we know that my X in this particular problem is 1. So I'm going to plug in 1. So when I plug this in, I'm going to use my calculator. Okay, so I'm going to do 25,000 times 1 plus 0.12, close parentheses, to the power of 1. And I get 28,000. Okay, so let's go back over here. So this would be 28,000. Okay, so that means I get to put this here. But see, that's going to take us a while, right? So this would be 28,000. So what I'd like to show you guys is that we can use our feature on our calculator called the table feature. So I'm going to clear this, and let's clear this. So now let's go to y equals. So I've already entered in the formula, 25,000 plus, or I'm sorry, times 1 plus 0.2. Now you could, change the 1 plus 0.12 to just 1.12 if you want, but I just left it like that so you could see it similar to the formula to the power of x. When I graph this, now many of you, when you graph it, you might not actually see it. So if you have this still, oops, let me go up here. So if this is -10, so most of us on our calculators have these numbers. So if I go to graph it, I don't see anything. So I think like it's broken or something. But in reality, what's wrong is these, remember, the populations already were at 28,000 and our graph is only showing from -10 to 10. So what we can do is we can go to zoom. So I click on zoom and I go to zoom fit. So what zoom fit does is it tries to do its best job on the calculator to fit our graph in the window we're seeing. So there you go. So that's, and again, this is the y-axis right in the middle. So it's showing us that, this y-intercept is probably 25,000, right? Because that's where it started at time 0. And then the next one over would be 28,000, at x equals 1, x equals 2. So they're showing us what happens. But we want to know at year 2. So what I'm going to do is I'm going to use this feature called second function table. So you see here where it's red on my calculator, that's the table function. So you see here, it gives me all of the values for x equals 1 or 0, 1, 2, 3, 4. So I can actually use this to fill in my table now. So let's go back over here. So for x equals 2, according to the table, it would be 31,360. For x equals 3, it would be 35,123. And then it would be 39,338, and so on and so on. So we could do that for all of these. So instead of having to do this, I could use this table feature on my calculator to answer these problems. But remember, you have to plug it into the y equals. All right. So let's go here. Now they want to ask a particular question of us. They want to know if this yearly increase continues, predict the city's population in 2025. Well, we know that the beginning year or year 0 was 2010. So I just do 2025 minus the year 2010, and that would give me 15. So for this problem, x is going to equal 15. So all I do, and that's what they have right here, is I'm going to use this formula, y equals c, but we know c is 25,000 times 1 plus 0.12 to the power of x, but we're going to use 15. So when we plug that in our calculator, we're going to do 25,000 parentheses 1.12 to the power of 15. And we get 136,839.144. But I believe they told us to round to the nearest whole number. So we're going to say y equals or approximately 136,839. Okay. Yeah. So that'll be a good answer. And this is an approximate rounding problem. Okay. So now here's the thing. You might say, well, why didn't we just use the table? We could have. I could have used my table. So let's go back to graph and let's go second function table. And let's just go down to year 15. 136,839. So notice the table's already kind of rounding for us. So you do just have to be a little careful with that depending on the level of accuracy you want. But that's the same answer that we just got doing our calculation, right? So remember, this is a very powerful feature for finding values, and you can change you know, how far apart you want the X's to be. You can use that in the step feature. So just remember, this is something that can help you if you're asked to find something quickly. You can just plug in the graph and do the table feature, and you can find values depending on where you want to find them at. All right, so let's go here. So let's go to another problem. So hopefully you guys are okay with that. Now we're modeling exponential decay. Okay, so everything's the same, but now we're going to be working with 1 minus the percentage, 1 minus R. Okay. So it says a quantity that decays by, a quantity that decays by the same percent at regular time periods is said to have exponential decay. So it says a large golf country club holds a singles tournament each year. At the start of the tournament for a particular year, there are 512 players. After each round, half the players are eliminated. How many players remain after 6 rounds? Okay, so let's see here. At the start of the tournament, a particular year, there are 512 players. After each round, half the players are eliminated. So each round, you lose 50%, right? So that's a percentage, and it's regularly happening on the equal intervals. So we're going to have our R is equal to 0.50 or 0.5. Let's see, C would be 512, right? Because there's 512 players. What else we got here? Well, and then we know the number of, it says how many rounds. So X will equal 6. So I can do this problem. I can just do, let me see here, Y equals 512 times. Now I'm going to do 1 minus 0.50 or minus 0.5. You know what? I should just do 0.5 to the 6th. And let's see what we get. So I'm going to do 512. So 512 times 1 minus 0.5 to the 6th. And I get 8. Okay, so then I just go back over here and I say this equals 8. So the answer to this problem would be 8. Now, if they ask me to turn into answer all these questions for the table, once again, I would just go to Y equals, and I would say 512 times 1 minus 0.5 to the power of X. And then we graph, and now we go into zoom fit so I can get a better look at this. Okay. There we go. So see how it's going, it's decaying, it's getting smaller and smaller and smaller. So let's go to second table. And you see right there, it says at, oops, let me zoom up, or not zoom up, but let me go up. So at 0, before it started, you have 512. You lose half of the people. So you're down to 256. You lose half again, you're 128. You lose half again, you're 64, so on and so on. And then by the 6th round, you're at 8. So I could have answered this question as well with the table. So this is something that I want you guys to practice, is getting better at using your calculator to kind of help you. But sometimes you do need to also know how to do it by hand. So make sure you also know how to use the formula. So let me see here. Let me just plug in the table. So this was 256. This was 128. This was 64. This was 32. The next one would be 16. You got it. So on and so on and so on. Okay. And then the next one would be 8. This would be X equals 5. And this would be X equals 6. All right. Okay. All right. So let's move on. So then it says we have something called a half-life. So basically half-life problems just say you have half of what's left. So that's what we just did. We literally said there's half of what's left. So let me see here. Let me make sure we have this right. So it says the half-life of a substance is the amount of time it takes for half of the substance to decay. So a form of DDT pesticide banned in 1972 has a half-life of approximately 15 years. So that means it takes 15 years for half of the substance to be gone, okay? So how much, and again, you could see why they ban it, that after 15 years, half of it is still left. How much of 500-gram sample of DDT will remain after 51 years, okay? So round to the nearest 10th. So here's what we're gonna do. Let's see here. So we know that X is equal, oops, hold on real quick. we know that X is equal to, let's see here, 51 years divided by how much of 500 gram sample DD2 will remain after 51 years. And it has a half-life of 15 years, right? That's the half-life. Okay, so this is approximately, let's take out our calculator. So we have 51 years, oops, divided by 15. So that's or that is equal to 3.4, okay? So what we're gonna do is normally we would say our X is worth, 3 or 4 or 5, but what they're saying is that our X value is 3.4 years because we're gonna say how many half-lives fit into 51 years, okay? So there's 3.4 of them. So what we're gonna do is we're gonna do Y equals, and then we're going to do 500 because they told us that's how much we started with, right? And then we're going to do 1 minus 0.5 like we did before because we're losing half of it. And now we're going to do X equals 3.4. So we should get on our calculator 47.4. But in case we weren't too happy with that, let's go put this in our calculator. So let's go Y equals, and let's go 500 parentheses 1 minus 0.5 to the power of 3. Oops, not power of 3.4. I'm sorry about that. The power of X, right? Because we're trying to graph it. So now we're going to graph. Okay, so we once again see it's decaying. And then we're going to do second function table. And we're looking for 3.4. So 3.4, do you see how it doesn't quite match what I want? So you see 3 is 62.5 and 4 is 31.25. So basically, this is where doing it by hand will help. But if we wanted to do the table in the previous problem, so we go second quit. So if we wanted to do the table, we know that there's 250 left, right? Because after 15 years, half of what was there, which was 500, half of that would be 250. Half of that would be 125. Half of that would be 62.5. Half of that would be 31.25. And then half of that would be not 156, 15.625. And again, just compare it to our table, right? 31.25, 15.625. But again, there's no 3.4, right? We don't have 3.4 here. So we could mess with the step. We could mess with the X step. You could change how much it goes by. Let me see if I could do that. Oops. Let me see if this would help. I don't remember exactly if this is how you do it. Graph, let's go second table. I think there might be a better way, but I think this might be okay. Nope. Yeah, I think I'm going to have to change the step size, but I'll show you guys how to do that on a different video. So what I did is I said, well, the table, which worked great when everything was nice and, 1, 2, 3, 4, that works great. But what happens when we kind of want to do something that's not quite perfect? So this would have an X value of 3.4. So remember, it says how much of a 500 gram sample of DDT will remain after 51 years. If they had said after 45 years, it would have been fine. If they had said after 60 years, it would have been fine. But because they said 51, once again, learning how to do it by hand and not just doing it with the table kind of saved me. So I get 47.4 grams, I believe, right? Okay. And that's how you can work with the table to solve these problems, or you can work with the, doing it by hand. You still end up using the calculator to do some of the powers and stuff like that, the exponents. But basically, I would consider this doing it by hand because you're literally plugging in the formula and then you just hit enter to get the calculator value. Okay. Using the table is, you're really not understanding what is happening per se with the calculation, but you're seeing that the graph is telling you these values. Okay. So hopefully that helps you guys get started on some of these problems. Please let me know if you have any questions in the next meeting, and I will see you in the next class.